Okay, so let's continue this course on ergodic theory. And so today I will go to the chapter 4, which is about ergodicity. Before that, I want to maybe spend half an hour telling you about the takeaway from the previous chapter, because I realize that there are many theorems that are written here and there. So I would like to give a takeaway from, tell you the takeaway from the previous chapter. So I will start takeaway from chapter 3. So again, let me recall that we are in chapter 3. In chapter 1, what we have seen, we have seen about dynamical system, invariant measures, and what invariant measure imply, which is one of the main things was the Poincare recurrence theorem, that point they tends to return infinitely many often when you have invariant measure. And in the second chapter, we have seen the existence of invariant measure under some structure on your space and also on your dynamical system, because if you remember, we were just considering measurable transformations. But if you add now like continuity, and if we have our space to be compact matrix space, we always have the existence of invariant measure. So today, and in the chapter 3 now, we went to to have a more implication of the existence of invariant measure, like these Birkhoff theorems. And if you remember, the first one we have seen was von Neumann ergodic theorem. It's funny that in this chapter we talk about ergodic theorems and we don't know yet what ergodic means. So you have an operator. So this is just a recall. So what I'm saying here, we have it already in the previous lecture. So I won't write all the details. We had them already written in the previous lecture. So this is a Hilbert space. This is a linear operator that is an isometry. Okay. And we have P, the projection to the I of U. So I of U is a set of invariant respect to U. And what we have seen is that the limit, the von Neumann theorem tells you that of I equals 0 n minus 1 U, so J here, UJV, this guy is exactly PV. It is the projection to the set of invariant guys for every V in H. Okay, as I noticed last time, this is a strong theorem. Like the result is strong. We have the convergence for every guy because we have more structure. We have more structure on our space. This is a Hilbert space. It's not any space, though it is infinite dimensional, but it's Hilbert. It has a norm. You talk about projection and so on. And this is an operator that is an isometry. That's also more structure. That's why we have this strong. So the main application of this theorem, what you should remember from the lecture, from this chapter, is that for H is L2 mu. So when you have a measure and a dynamical system also, and U is a Koopman operator. U equals UF, Koopman operator. Okay? So Koopman meaning that U, F composed with C at C. So if you apply U of C equals C composed with F. So fixed point of this Koopman operator are invariant functions by the dynamics. Okay? And what we have seen, if you apply this theorem, this operator is an isometry. This is a Hilbert space, 1 over n, J equals 0 to n minus 1 of phi composed with Fj is converging L2 mu to the projection let's denote it like this, the projection to the set of invariant guys, okay? And yeah, so as I said, this seems like to be a strong, results, but, strong in one sense, but also weak in another sense, that it gives this convergence is L2, okay? Like this convergence, you don't have a pointwise convergence, okay? That's why we needed another ergodic theorem, which is a Birkhoff ergodic theorem. So in chapter 2, in the next section, another takeaway from chapter 3 is Birkhoff ergodic theorem. So for this, we have two types of Birkhoff ergodic theorem. First, we have a subadditive ergodic theorem. Or this we call it also Kingman theorem. And now how does it work? You have, if you remember, we have our dynamical system, and we have mu is F invariant. So as I said here, yeah, this convergence is just L2, and in this theorem you don't see any measure playing in. And we want to improve this by having like a type of pointwise convergence. That's why here we need a measure, for instance. And if we have phi n over n, phi n is subadditive with respect to f, meaning phi n plus m, phi n plus phi m composed with fn. So this is subadditive with respect to f, with respect to f. Okay, so, and that there is another condition that the first one is L1, because this will guarantee with subadditivity that all others are in L1. Is integrable. So if you have this, the theorem tells you that phi n over n is converging to phi tilde mu almost everywhere. And phi tilde here is invariant by the dynamics n. Phi tilde composed with f equals phi tilde, meaning phi tilde is also a fixed point of the Koopman operator. Okay, and we have seen that the integral of phi tilde equals the limit when n goes to infinity of 1 over n, the integral of phi n. So d mu. Okay. So this is a very important in theorem, which is a subadditive ergodic theorem, and it gives, for instance, Birkhoff ergodic theorem. And yeah, so Birkhoff ergodic theorem. So under these assumptions, I have it already. We have it written already last lecture. So this is just, I'm reminding it. N minus 1 of C composed with Fj of x. This is converging to phi tilde, some phi tilde of x, and phi tilde is is measurable for mu almost every x. Yeah, and the integral of phi tilde is the limit of these integrals, and we have seen, like we have the proof of Birkhoff. We deduce it from this theorem, because you can see that this sequence here will be subadditive. If you choose this as your phi n, it will be subadditive. It satisfies the condition of the subadditive ergodic theorem. So you can see Birkhoff as an application of this ergodic this Kingman theorem. As I said last time, in the literature you might see, direct proof of Birkhoff, which is similar to the direct proof of the Kingman's theorem. And you can see also in the literature Kingman's theorem, the proof of Kingman theorem uses Birkhoff theorem. But for this lecture, this is how we do it. We prove Kingman, and then we have Birkhoff from this one. Okay? And the applications, there is another point, which is application to Lyapunov exponents. This was very important. Lyapunov exponents. So this was Furstenberg theorem. So which was, if you have a cocycle, so you have a cocycle, which is, so you have a way to choose, you have from M to, let's say, GLD. This is a space of matrices. And you have theta, which is this. And you have a dynamical system. And you define phi n x equals theta at fn minus 1x until theta of x. So this defines a cocycle over f. F is a dynamical system. So remember, f is from M to M. Okay. Furstenberg tells that 1 over n, the sum, the log of the norm of phi n x is converging to the biggest Lyapunov exponent for mu almost every x. Mu almost every x. So you have this function, which is the biggest Lyapunov exponent, which is a measurable function on your space. And similarly, you also have 1 over n log of phi n x minus 1 is also converging to the minimal Lyapunov exponents for mu almost every x. Okay. Yeah, so this also, you just get it from an application of this subadditive ergodic theorem. Okay, because you can see that the norm of the matrix is less than the product of the norms, and then with log you have the product, log of product is the sum of the logs, and then you get subadditivity. Oh, I forgot, there's a condition that theta should be integrable. Okay, the norm of log of theta is in L1. Okay, and you have, of course, you have mu that is F invariant. Okay, so this is just a recall. We have it in the course. And there is an exercise actually which is interesting that I would like to discuss a little bit about these Lyapunov exponents and how it relates to Lebesgue when you have invariant measures. So if you have M is a surface, I just do dimension 2 here, but what I'm saying here, it generalized to higher dimensions also. If you have a surface and f from M, oh, by the way, I forgot. Yeah, I don't need to recall that, otherwise I might be repeating the last lecture. Is a diffeomorphism. So diffeomorphism meaning that it is C1 invertible, and the inverse is also C1. And M is a smooth surface, okay? At least it is differentiable so that I can talk about diffeomorphisms. So if F preserves Lebesgue, then lambda mean x plus lambda max of x is 0 for mu almost every x. Like if you have a diffeomorphism that lives invariant Lebesgue, the Lyapunov exponent, they are opposite. Like one is opposite. You have two Lyapunov exponents. One is positive and the other one is negative, and one is minus the other. Okay. As I said last time when I was doing the introduction of these Lyapunov exponents, I was telling you that like Fussenberg's theorem is a way to do what we have as, you know, as eigenvalues of a dynamical system when you have a nonlinear system. Okay, so these eigenvalues for a matrix, like if you had here a linear space and F was just an application like a matrix that you're applying. If F was just, if this guy was just the same matrix, sorry. If this guy was the same matrix that you're applying, and so this will be just the log of the eigenvalues. And if a matrix, you know, a matrix lives invariant Lebesgue if the determinant is 1, that we know. A determinant being 1, you see that the eigenvalues they add up to 1. So the log of the sum is 0. Okay. Sorry, the product is 1, so the log of the sum is 0. So this is just along those lines, okay, for a nonlinear system. So, and yeah, this has, you know, many applications in dynamical systems. Like there are many systems, like if you want to know whether you have a positive Lyapunov exponents or a negative Lyapunov exponents, it's just enough to see it lives invariant. You know, if it lives invariant, a smooth measure, or some people might call, like, if it is conservative, okay? So conservative system, they have this property that the Lyapunov exponent, they cancel each other. Like this is example for geodesic flows and many also contact flows also. This theorem is general, okay? You can do it for n dimension. In that case, you will have the sum of the Lyapunov exponents times their multiplicity is 0. But for this course, we did not define the other Lyapunov exponents. So this theorem, it just gives you the biggest and the smallest. So the smallest and the biggest. So in the middle one, there are ways to find the middle Lyapunov exponents, which is the Osler-Detz theorem. But for this course, we don't do it. So that's why I just write this exercise for surfaces. And as I said, the idea, I will just write a hint here, and maybe on Friday you can discuss it with Mateos. The hint is what? So we have seen that preserving Lebesgue. So remember, we have seen this exercise. F preserves Lebesgue is equivalent to the determinant of df is 1 for all x in M. So if you preserve Lebesgue, you leave the determinant is 1. We have seen this, so we have seen how to do this. Yeah. So the determinant of f is 1, so also that the determinant of dfn x is 1, because the determinant is multiplicative. Okay, when you take the composition, is a product of the determinant is 1 for all x. So you can see that this matrix here is invertible. Okay, so you can, if you want, you can write a normal, this Jordan form. So you can write dfn x as jn x minus 1 composed with a n x composed with jx. Okay, you can write the Jordan form of this matrix. What is important here, like the step of the proof, the proof consists of saying that, so already the determinant is 1, so the eigenvalues here for this matrix, their log, they cancel. This matrix, the sum of the log of the eigenvalues is 1, okay, for this matrix. Yeah, so which is, so they have, the determinant of this one is 1, and it is a diagonal matrix. Okay, this guy is diagonal. Okay, so I'm just giving a hint, after you can fill in the details. And so you can see that the Lyapunov exponents of this cocycle, df, is the same as the Lyapunov exponent of this cocycle now. This guy here that you have. Okay, up to some technicalities. So there are some technicalities you need to handle here. Is that you can write this in a way that the norm of these matrices, these two, their norm is bounded above and below. You can write it so that this guy has norm bounded and below. And a trick to use here is that in the definition here, you divide by n, there's a log. So if you put here a constant, you don't see it at the limit because you divide by n. So you can choose these two matrices by just dividing and multiplying and dividing and multiplying. What you divide and multiplying, you put it here so that this matrix has, certain nice property that the norm is bounded above and below. This guy, the norm is bounded above and below, and you can see that the limit will be the same as the limit of these guys, and these guys at each end, they satisfy this property. Okay? Basically, that's the idea, okay? Yeah. So you can continue this. You can do the details on Friday with Mateus here. Do you see what I mean? So there is one property about Lyapunov exponents that is, for instance, so this remark would just explain what I'm saying. The Lyapunov exponent doesn't depend on the norm you choose. Okay? So see that here, I choose a norm here. But if you take another norm that is equivalent to this, you get the same Lyapunov exponents. Let's write that as a remark. Maybe that will help to explain better what I'm saying here. So remark, so Lyapunov exponent doesn't depend on the norm. On the norm, because if you take another norm, if you have two norms, so let 1, and you have two norms that are equivalents, okay, because we are in a finite dimensional space, everything is, so these two norms are equivalent, meaning the norm 1v is greater than c minus 1 norm of v2, which is less than c norm of v2. So if the two norms are equivalent, so you see what I'm saying. If you in here, if you plug 1 or 2, you get the same limit, because what you get is the norm log of the norm of Vn x1. This guy is less or equal to c, which is log of c plus log of the norm of Vn x2 So if you divide by n, this guy will go to 0, okay? And this guy will converge to, so you will have the Lyapunov exponent with respect to the norm 1 is less than the Lyapunov exponent with respect to the norm 2, and you can do the same. 1 and 2, you can reverse this inequality, okay? That's what I'm saying here. That's the same type of trick you need to do here. That you can put matrices here for which their norm are bounded above and below by a constant, and that constant will not change the Lyapunov exponents. And we know the Lyapunov exponent for this cocycle, they satisfy this property, okay? So this is, I will close chapter 2 here. Chapter 3, sorry. Yeah, by the way, there is one thing I forgot, a reference I forgot to give. So because this weekend I got an email from somebody who is following this course that I mentioned a book to study the parent-Frobenius operator. So this is a reference I forgot to give. I promised I was going to give it, but I forgot. Reference for parent-Frobenius operator. So this is not part of this chapter, okay? It's just a reference I was supposed to give. I have to give it now before I forget. There is this book by Lazotta and Mackay. The title of the book is Chaos, Fractals, and Noise. So it says stochastic aspects of dynamics. So this is the book. So if you really want to study these properties in like using functional analysis, this is a good book to look at, by Andre Lazotta and Michael C. Mackay. So this is a good book if you want to read about parent-Frobenius operator and also the Koopman operator. It has a lot of, yeah. So for instance, you can see a lot of ways to see mixing, ergodicity, this stochastic property using these operators, okay, using the parent-Frobenius operator or Koopman operator. Also, if somebody is interested in having a seminar at the end of this lecture, there are good topics for seminars in this book, okay? So this was just a parenthesis. I said half an hour, I'm on time. So I will start now chapter 4 about ergodicity. So this is basically the takeaway from the previous chapter. So remember, yeah, the application of these theorems, one is the Lyapunov exponents, and remember that conservative system, we have that relation for the Lyapunov exponents. So preserving Lebesgue, we mean conservative, okay? For conservative system, invariance has an implication on the Lyapunov exponents. So we will start chapter 4 about ergodicity. So if you see everything that we were doing in the previous chapters, it only requires invariance. Everything, you just need invariant measure, okay? So I will recall what we have seen. But, I just said Birkhoff ergodic theorem. I have it here, and I will use some notations from the previous chapter. So in this chapter, we suppose also that we have M, B, mu. This is our measured space. Okay. And also Yeah, I will suppose that mu is f invariant. So I have f from m to m that is measurable. Okay, and mu is f invariant. Okay, so these are my assumptions. Though ergodicity, you can do it without supporting invariance, but for this course, when we talk ergodicity, we mean for invariant measures. Okay. Yeah. So previous chapters, just with this, we have some implication. Now we want to add more structure to our measure to see what are the implications we have. The structure is ergodicity. So let me recall remember, so given a measurable set, remember tau x, tau ex, with the limit when n goes to infinity of 1 over n, the cardinality of j in 0, we can just do it because now we are in the spirit of time average and space average. Let's just write it like this: j equals 0 and minus 1 of the indicator function of E along the orbit. Okay. So this function exists because of invariance. Okay, this is the Birkhoff theorem. Okay, this is this theorem. Invariance tells you that this function exists, and so I'm just setting up some notation, and the integral of tau E x d mu is just the measure of E. That's all we get from invariance. And there's another remark here that tells you that this function is invariant along the orbit. So tau E x is f invariant, meaning tau E x equals tau E f I x. Okay? Again, it is a fixed point of the Koopman operator, if you want to look at it in that way. And there's another remark, which is just, the version using integrable function. So, yeah, which is what I have there. So I want to, phi tilde, so j equals 0 and minus 1. Almost every x. So basically, we want to improve these results you get from invariance in this chapter. And mu is f invariant also, that phi tilde is f invariant of x equals phi tilde composed with fi x. Okay. So this is what we want to improve basically here in this, by adding a structure on our measure. So definition. So this is a definition of ergodicity. F mu is ergodic if this function is constant, this guy here, if tau of E x equals the measure of E. Oh, by the way, I forgot. I'm interested in finite probability measures. Okay, measure I'm choosing here are probability measures. Finite measure normalized 1. For mu almost every x. And for all E measurable. Do we know an example of dynamical system with a measure that is ergodic? Do you know of an example? Just from this definition. So for instance, if you have a fixed point on your dynamics, you take a Dirac delta. Okay? If you take a Dirac delta, you can check that the Dirac delta is ergodic. But before, let me maybe do a characterization of this so that it will be, easier to handle the definition. So let's write the characterization. Let's write this proposition, which gives a characterization of ergodicity. So the characterization tells you that F mu ergodic is equivalent. Sorry. So if F mu is ergodic, then the following are equivalent. What are the following? Okay, so this is a definition. Tau, the mean sojourn time, is constant and is a measure of E for mu almost every x. Okay, so I'll be writing a lot of trivial things here. Tau E dot is constant, which is just in there, is constant for mu almost every f. C is that for every phi, if you start with an L1 function, you have phi tilde. Phi tilde is, that's why I was introducing this notation, okay? Phi tilde of x is the integral of phi d mu for mu almost every x. So for instance, this property, which is equivalent to ergodicity, tells you that time average is converging to space average. Okay, time average here. Here you could not say yet it is converging to space average, just converging to a function. But ergodicity will tell you that this function is constant for mu almost every x, and that constant is just the space average, which is the integral. Okay. So I'm assuming I'm with probability measures here, C and D. Yeah. So phi in L1, then this guy is constant, which is, you know, just along the same line as this. Phi tilde, as these two are, you know, the same, we consider these two. So phi tilde is, just for completeness, we are writing for mu almost every x. Phi tilde is constant. For mu almost every x. E is important here, that it is a characterization that if phi is in L1 of mu and phi is invariant, because fi, because phi for every I, this implies that phi is constant. So this implies that phi of x is the integral of phi d mu, okay, for mu almost every x. This is a characterization of ergodicity that tells you that invariant functions are constant. Like fixed point of Koopman operators are constants. So let me write the two others here. F oh, what did I write? So invariant function are constant. Is f minus 1. This is the definition that people use for ergodicity, which is, you know, more explicit than this one, because this one is maybe difficult to think about because, okay, this is a means, usually it involves some limits, but here it tells you that implies, I don't know why I'm changing, implies that mu of A, mu of E is 0 or mu of U is 1. Like invariant set are full or negligible, full measure set or negligible, okay? Yeah, most of these properties are just, they don't require proofs, okay? Most of these guys, they don't require proofs. So, so let's just, for the proof, let's just do a diagram here. So we're going to prove that all these are equivalents. So I have A, I have B, I have C, I have D, I have E, I have F here. So to prove that they are equivalents, you just need to prove that this diagram is simply connected, and this graph is simply connected, and at every point you have you know, an exiting arrow and an arrow that is entering. So A implies B is easy, right? A implies B is easy. So yeah, so this is constant. Okay. And there is another error, which is B implies F. Let's see how B implies F. Because F is, you know, the usual definition that people use. So why? So this one is easy, okay? This one is easy. So let's see why B implies F. So you have B, you want to take, now you take a function that is a set that is invariant. So let E of E equals E. So B tells me that tau x of E equals constant. Okay? And you can see that if you take a point for x in E complement, for x not in E, you can, by invariance, by this set being invariant, you can see that tau of x A is 0. Okay. So this tells you that, so since this is constant, so this implies that mu of E is 0 or 1. Okay? Yeah, this is easy. And see that we have F implies E. F implies E. What is F? F implies E. Yeah, E tells you that invariant functions are constant. Yeah, so you want to prove that this function is constant. So let's see why F implies E. So to check E, you take a point, you take a phi that is in L1 mu, and you suppose that phi is F invariant. Phi composed with Fi equals phi. Now you want to prove that this guy is constant. Okay, so the way to check this is, yeah, we're going to use this property. You use this family of, so for C, for a real number, you define BC, this set, as the set of points such that phi is less or equal to C. Okay. By this property, so phi composed with Fi equals phi imply that this set is invariant. F minus 1 of BC equals BC, right? And F tells me that F implies that mu of BC is 0 or 1. Okay? So these sets, they have 0 or 1 measures. And if you so if you can see also that this is non-decreasing, these sets. Like if C1 is greater than C2, this implies that BC2 is a subset of BC1, and the measure of BC2 will be less or equal to measure of BC1. Okay, and these guys, let me just continue the proof here. We continue here. These sets, they have 0 or 1 measure. So there will be one which has 1 measure, because the union will be the whole space. Okay, so there exists C bar says that mu b C bar is 1. And mu of b c is 0 for all c strictly less than C bar. Okay. And this would imply that, and yeah, you can check that by definition. You can check that phi is exactly C, because after C bar, that set has measure 0. Okay. So then mu phi equals C bar for mu almost every x. Okay? Because if you're bigger than C bar, the measure of the function between C bar and C is 0. So let me write what I'm saying here. So what I'm saying here is that if you have C tilde bigger than C bar, the measure of C in C bar C tilde is 0. You know, this set of C strictly less than C bar C tilde is 0, because the measure of this guy is already 1. So this guy has 0 measure, then phi is constant. Okay. Yeah, basically this is one that needed some doing, but all the others are trivial. Okay, all the others are trivial. Let me just, for completeness, let me do it here. You can see that D implies B. D implies B. You take just the function to be the indicator function of the set E. And you can see that C implies A. C implies A. Yeah, same reason. So if you have the indicator function here, this will be the measure. That's also easy. You can also see that E implies B. So yeah, so these two, we need more arrows on these two. You can see that C implies, or E implies C, yes. This guy, you can see that E implies C. Yeah, it's obvious. Yeah, I think this guy needs more arrow to complete the equivalence, which is D. And also D is equivalence to C also. This is, yeah, it's the same. D and C is the same. It's just, yeah. Yeah, from everywhere you can go everywhere. From A, you can go to B. From A, you can go to C. How do you go to C? You go B, you go F, you go E, you go C. And from A, you go to D, this way. And then this way, and this way. And from A, you go to E, this. E, you go to this guy. You can check that they are equivalents, okay? Only these two needed some proofs. So now, as I was saying, you can look at examples and non-example, like non-ergodic guys. So just to find examples, it's easier to think of this as a definition. Okay, think of this as your definition. And this is just saying that if you have your space, non-ergodicity, if me not ergodic, this is just saying that you can decompose your space. So this is someone saying decomposition. That, or like, you can, ergodicity, you can see it as like irreducibility of your dynamics. You cannot find two meaningful dynamics inside this one. So you can think of this E complement. If you have non-ergodic, that means that you have here an invariant set. So here you can think of having a dynamical system, and also here you can think of having another dynamical system. In some way, non-ergodic means that you can decompose your dynamics into two dynamical systems. And as we will see that you can always, even if the measure is not ergodic, you can make a decomposition into ergodic components. Okay, like here, maybe if you do this decomposition, this dynamical system will be ergodic, and this one will be ergodic. Like, think of like having to write a number into decomposition into prime numbers. Okay, think of having ergodicity. It means that you cannot decompose your system into, the system is irreducible. Okay. All right, so let's go to more. Yeah, I need to get to the circle rotation is ergodic. I need to get to that point. So let's write another proposition, which is again a characterization of ergodicity. So if you have a dynamical system, and mu is F invariant, so the following are equivalents. So always trying to find characterization of ergodicity. So when we talk about ergodicity from now, you can take any of these as your definition. Invariant functions are constant. Invariant sets have full or zero Lebesgue measure. The mean sojourn is constant. All these you can consider as definitions. So F mu ergodic, B is for any two measurable sets, you have 1 over n, the sum j equals 0 to n of mu of fja intersect b is converging to mu of a times mu of b. Okay. C that for every C in LP and Xi in LQ, where P and Q are conjugates, okay? 1 over P plus 1 over Q is 1. Then 1 over n, the sum j equals 0 to n minus 1 of the integral of UF. UF is the Koopman operator, okay, associated to F. This guy is converging to phi d mu, C d mu. These are also like some type of statistical properties that you derive from ergodicity, because if you're familiar with probability, this is type of saying, independence of these two events, being in A or being in B, with respect to this dynamics. Okay. And this is a, similar to this one. This is using sets, this is using function. These two are, this is a function version of this one. Okay. Yeah, this is, these are like interesting properties in dynamical system. Think of just this one probably, which is easier to see, which is easier to get some intuition about. So this is really telling you that ergodicity has something to do with a type of mixing of your system, though we haven't defined mixing. Mixing means that, these orbits is going kind of, anyway, I will not, what I'm saying is not very rigorous. But looking at this property, one might think that ergodicity has something to do with, having a dense orbit, or, and if time allows, or if someone is interested, there are some nice topic for seminars, examples of dynamical system which has a dense orbit and is not ergodic. There are some nice examples on this and good for seminars or so. So let's try to prove this, and then proof as I said here, this is a specific example of this one where you take C and psi are indicator functions. So C implies B is obvious. C implies B. This is obvious. We just take C equals indicator function of A, and C indicator function of B. So B implies A is also not difficult. B implies A. What is B? Yeah, B implies A. You take A equals B, and what you get at the end is mu square. A equals B. So if you have f minus 1 of A equals A, this means that the sum j equals 0 n minus 1 of mu of f minus 1 f minus j A intersect with A. This is just n mu of A because it's the same. This guy is A, and yeah, so nothing to say. So if you want, you can write it like this. So you would have that mu of A equals mu of A squared. This tells you that mu of A equals 0 or 1, which proves ergodicity using F as a definition. Okay, now let's see how A implies C. A implies C. So already by Birkhoff, we have 1 over n, the sum of u f u of j psi x is converging to phi tilde x. Okay, this is just Birkhoff theorem using invariance. And if you use ergodicity, you have that this is just the integral of phi d mu. This is ergodicity. Okay, for mu almost every x. In proving C, we are interested in multiplying by C. Multiply by C. So this is what we want to look at. UJF at C x times C d mu. See that already if your function C was essentially bounded, if this guy was essentially bounded, you can use the dominated convergence theorem in this guy, because you know this will converge to a constant. So if C is in L infinity, meaning Q is infinity, okay, and P is 1, then so dominated convergence theorem will, because this function is converging to 1. Okay, let's do it here. This guy is converging to 1 and dominated, so it is converging to the limit of this guy times the integral, and the limit of this guy is just the integral, okay? Dominated convergence theorem. Gives the result. So if we don't have this essential boundedness, what we do is we use a type of monotone convergence by truncating this function. Okay, so if C is not essentially bounded, so we use this sequence Ck of x equals k if Cx is, is bigger than k equals Cx, and phi x is in between minus k and k, and then minus k is less than minus k. Okay, so this is a sequence, and you can check that this sequence is converging LP to C. So Ck x, Ck minus C LP is converging to 0. This is because these sets of points, you know, they have their measure going to 0. The set of points where, yeah, so this gets closer and closer, LP, to this function. So, so this is just saying that for every epsilon positive, there exists k, such that k epsilon, k bigger than k epsilon, imply this is small, okay? It's less than epsilon. So you just write this, you write this integral ck minus c. This is less or equal to one over n. You use this Haldo UIF ck minus c p. And this guy is less than epsilon for k large enough. And what you do is you replace, you add and subtract. So you write this 1 over n the integral of u f I c times psi d mu minus the integral of phi integral of c. This guy will be less or equal to, you add and subtract ck 1 over n the integral of u f I ck minus c, so c minus ck c d mu plus the integral of 1 over n the sum u I f ck of c d mu minus the integral of phi the integral of c. And you can see that this guy is less than epsilon because this guy is essentially bounded. This guy is essentially bounded. And also, this guy is less than epsilon. So you will have, at the end, this is less than 2 epsilon for k large enough. Okay? And the right-hand side doesn't depend on k. So I have 15 minutes. I can now prove here just that, close here, that the circle rotation is ergodic when you have irrational angle, rotational angle. So example. So you can see, so the circle rotation is our first example. R theta, so you have R theta that is defined from S1 to S1, which takes Z, which is E 2 pi I x, and gives E 2 pi I x plus theta. You just rotate by theta. So proposition. If theta is irrational, then R theta is ergodic with respect to Lebesgue. With respect to Lebesgue. Okay, Lebesgue. Let's write Lebesgue as M. So you should in this course, you should think of the examples that we have been doing so far. We have been, I've been giving some examples like contraction map. You know, when you have x gives a half of x, where everything is going to shrink to a point. We have seen example of decimal expansion like kx mod 1. We have this type of examples. These three examples, you know, they really, you know, represent the most system we can have. This is a contraction map, this is an expanding map, and this is a map where you don't have contraction. It's just like a translation, okay? Yeah, and yeah, here we this is a typical example of system where you don't have expansion because the derivative is 1 everywhere. And in the next lecture, we will see how to do with systems when you have these two behavior, contraction and expanding. We will do like a hop argument. So, but for this example, you don't need any hop argument. Actually, hop argument doesn't apply to this. We will see that later. So let's prove this. Again, I say something to keep in mind is, you know, the relationship between ergodicity and like what we say topological transitivity, like having a dense orbit. Okay, I said earlier that there are nice topic for presentation at the end of this lecture, that having a dense orbit doesn't imply ergodicity, and also ergodicity doesn't imply having a dense orbit also. In this course, we will see that ergodicity will imply dense orbit on the support of the measure. And it speaks to the support of the measure. But the support of the measure might not have any, you know, topological meaning. You know, might not see anything about the topology because the support might not have even an open set for some measures. And this is an example we have seen in the previous lectures, that this is an example where every orbit is dense. Okay. Theta is irrational. Okay. Every orbit is dense. So let's see how do we solve it. So as I said, we can use any definition of ergodicity. Here we will prove that invariant functions are constant. So let's see in L2M. So Lebesgue is denoted by M, that is invariant. F invariant, that is R theta invariant. Okay. So when we want to prove ergodicity, we can use any of those A until F, those properties. So here this one is easier to do here. There's something interesting on using this space because this space has a countable basis. Okay, so L2 has a countable basis. So L2 function on S1. Okay, meaning this function C can be written as ak exponential of 2 pi ix, like this. Sorry, yeah, I'm doing it on the complex. So C is a function from S1 to, because I use S1 as a subset of the complex, to this guy here. So sum over k ix. So this is a basis of this space. This family here is a countable basis of L2. So what does invariance mean? So this is phi of x, sorry. X or z, sorry, I said I mean, yeah, x or z. I mean, okay, I should be more e 2 pi I x. So this is because this family is a basis. Let's write it. Phi kx ix basis of R to M. So phi R theta invariant. This implies that phi of R theta equals of 2 pi Ix equals phi at 2 pi 2 pi Ix. Okay, and this you can write it as a sum of AK exponential. When you apply R theta here, it is, so let me do it like this before, of E 2 pi I x plus theta. Okay. And this is the sum of AK exponential of 2 pi ki x plus theta equals the sum AK of E 2 pi k I x. I think that's correct, yes. And this, if you want to write it as a k in terms of the basis, you can take out E 2 pi k I theta times E 2 pi k I x. It's the same thing here. So you write two functions in this basis, so their coefficients should be the same, okay? So this guy should be the same as this guy, okay? Because this is the basis of L2. So you have AK E 2 pi k I theta is AK. For every k. So if there exists at least one k naught that is non-zero, you can divide. If a k naught is different from 0, so what you would have is this is 1, E 2 pi ki theta is 0 for k naught. So k naught should be bigger than 1 here, because if you want to use this for k equals 0, it is obvious, okay? For k equals 0, it is obvious. It is 1, sorry. So for theta being irrational, that means that this is never 1. But theta is, so that means that all the k are 0 for k bigger than 1. So this implies that AK equals 0 for all k bigger than 1. So that means that this function is A0. So that's 0 for me for M Lebesgue almost everywhere, because when you write in this basis, it is Lebesgue almost everywhere, okay? Lebesgue almost every. Okay. So this is just an easy direct proof of ergodicity of the circle rotation using just the characterization of ergodicity by invariant functions are constants. So as I said, this is an example of a system that doesn't have any chaotic behavior, if you want to say, or yeah, doesn't have any chaotic behavior. Like the derivative is 1, you don't have any expansion or contraction, it's just a translation. So in the next lectures, we will see a method to prove ergodicity for other systems, which is called the Hopf argument. And also we will discuss a little bit about ergodicity and having a dense orbit, like transitivity, how they are related. As I said, there are examples of systems that has a dense orbit and that are not ergodic. But we will see that if you have ergodicity, you have a dense orbit restricted to the support of the measure. Okay. You can in some sense you can see ergodicity as a type of transitivity in a measure theoretic sense, like restricted to the support of the measure. But the problem is the support of the measure might not have any topological interesting properties, like doesn't contain an open set, doesn't have interior or something like that. Yeah, but for Lebesgue, it's good to have Lebesgue being ergodic. At least it's something interesting. Anyway, so I will stop here for today's lecture, and I will see you on Wednesday.